You've seen the pictures, right? The sleek electric air taxis gliding over cities. It's an incredible promise. But it all comes down to one absolutely massive question. How do you prove that a brand new, revolutionary power system is safe enough to fly right over our heads?
All right, let's break this down. The situation is pretty clear. We've got this incredible new hybrid engine, the P13, that could totally change how we travel between cities. But here's the complication. The old ways of testing engines, they just don't work here. They're dangerously outdated for this kind of complexity. So the resolution? Well, that means we need a whole new playbook for proving safety, starting from the very first line of code.
Look, we're not just talking about a bigger battery here. The complexity of this P13 system is, well, it's on a whole other level. Think of it like a really intricate dance between a combustion engine, a bunch of electric motors, and these super fast clutches. A traditional jet engine is all mechanical links, right? Predictable. This is a web of software telling everything what to do, second by second. It's something aerospace has never, ever had to certify before. So to get this thing certified, the safety target is just staggering. It's 10 to the minus 9. What does that even mean? It means less than one catastrophic failure for every billion hours of flight. A billion. Let me put that into perspective for you. Imagine you have a fleet of 10,000 of these things, flying 24/7. You'd only expect to see one of these failures about every 11 years. That's the standard. That's the bar. And you absolutely cannot get there by just winging. And that brings us to a really crucial point. The old way of doing things? It's over. It's officially dead. You can't just build this complex machine, bolt it to a test stand, and cross your fingers. Not when you're aiming for a 1 in a billion safety target. That old build it and break it mentality is way too slow, way too expensive, and honestly, it's just too reckless. So how do you tackle that kind of complexity? You need a new philosophy. You need a master plan, a systematic framework for designing, building, and testing that ensures every single decision you make is deliberate, traceable, and most importantly, verifiable. And that brings us to the hero of our story, the V model. This isn't just some corporate flowchart. It's a super rigorous framework straight out of the aerospace standards. It forces a really simple but incredibly powerful rule on you. For every single requirement you write down, you also have to write down exactly how you're going to prove you met it. No assumptions. No, we'll figure it out later. Everything has to be proven. It's actually pretty elegant how it works. You start at the very top with the big picture needs of the aircraft. Then you travel down the left side of the V, breaking that big idea into smaller and smaller pieces, all the way down to the tiniest component. Once you're at the bottom, you start the climb back up the right side. You build, you test, you verify each piece before integrating it into the next level up. You prove the little things work before you even try to build the big thing. Okay, so climbing up that right side of the V, how do you actually do that? Well, engineers use this brilliant strategy called the verification pyramid. And the whole idea behind it is something we call shifting left. It's simple. Find your problems as early as you can when they're still cheap and easy to fix. Think of it like this. You build a pyramid of tests. You start at the bottom, in the virtual world, with cheap, fast simulations on a computer. Then you slowly work your way up to the really expensive full system physical tests at the top. The goal here is genius. Use those cheap digital models to find and squash more than 60% of all your design flaws before you ever spend a dime on manufacturing real expensive hardware. Right at the bottom of that pyramid, we have what we call MIL and SIL. That's model in the loop and software in the loop. Basically, we're testing the system's brain, the control logic, in a purely digital world. Once that looks good, we take one step up to CHIL, or controller hardware in the loop. This is where we take the actual physical flight control computer and plug it into our simulated world. We're seeing how the real brain reacts to a fake universe. And let me tell you, this Hill setup is a total game changer. It's like a safe virtual playground where we can be really mean to the flight controller. We can throw hundreds of crazy fault scenarios at it. What happens if a sensor fails? What if a communication line just drops out? What about a short circuit? These are things you could never safely test on a real aircraft flying in the air. It would be way too dangerous. Okay, so after thousands and thousands of hours in that virtual world, after we've tested every scenario we can think of, only then is it time to build the real thing. We're finally at the top of the pyramid. These are the final exams on the ground. And this is where we meet the heavy metal. On the left, you've got the Copper Bird. It's a full-scale replica of the entire high-voltage electrical system.
Think of it as the aircraft's entire nervous system. And on the right, that's the Iron Bird. It's literally the entire P-13 powertrain. Engine, motors, clutches, the whole shebang, laid out one-to-one, like it's on an operating table ready for a pre-flight heart transplant.
Now, the Iron Bird has one job that's more important than any other. It has to nail the critical mode switch. This is that key moment when the aircraft goes from super quiet electric flight to firing up the engine for a long cruise. For the passengers, it has to be completely seamless. No flicker of the lights, no sudden lurch, nothing. And to prove it's totally reliable, the Iron Bird is going to perform that exact maneuver over 5,000 times. So you can imagine all this testing, virtual and physical, it generates billions of data points, just mountains of it. But data by itself is just numbers. It's not permission to fly. So how do you turn all that evidence into what we call certification credit, the official stamp of approval from the regulators? Well, it's a really disciplined three-step process. Step 1, you have to hit your non-negotiable performance numbers, what we engineers call the red line metrics. Step 2, you've got to prove your hardware can survive the absolutely brutal environment of real flight. And finally, Step 3, you have to meticulously connect every single piece of your test data back to the specific regulations. Let's talk about those red lines. First up, mode switching. Any transition, say from electric to hybrid, has to happen in less than 200 milliseconds. That is literally faster than you can blink. Why? So there's absolutely zero lag or power drop that a pilot or passenger could ever feel. Next up, thrust response. When the pilot pushes the throttle, the system has to respond in under 50 milliseconds. That's for immediate, crisp, predictable control. You absolutely need that, especially if things go wrong. And this one is the most critical. If there's an emergency, the high-voltage safety system, the kill switch basically, has to cut all power in less than 10 milliseconds. There is absolutely no room for error on that one. Then comes the hardware abuse. I mean, we literally torture this stuff. We shake it violently to simulate being right next to a running engine. We stick it in a vacuum chamber to see how it handles the thin air at 25,000 feet. Because guess what? Electricity behaves differently up there. We even blast it with electromagnetic energy to make 100% sure it won't mess with the plane's navigation systems. And at the very end of all this, all that evidence gets organized into a compliance matrix. This is the big kahuna, the final report for the regulators. It's an undeniable, traceable paper trail that says, here's regulation 1.2.3, and here is the exact test data that proves we met it. It connects every rule to real proof. So, after this whole incredible journey, from a line of code, to virtual models, to physical torture tests, to billions of data points, what do you get? The result is confidence. It's not just hope, it's not ambition. It is cold, hard, data-driven, verifiable confidence. It's the confidence to put this machine in the sky, over our cities and over our homes, knowing that its safety isn't just a dream, but it's built on a foundation of billions of proven data points. So I have to ask, does knowing about all this immense rigor that goes on behind the scenes, does it change how you see the coming age of electric flight? Because this process, this blueprint for safety, is the bridge that connects a bold idea to a safe reality. It's what ensures that the future of flight is not just innovative, but fundamentally, verifiably safe.